So this is linear algebra, page 255, number 3. So in the vector space R2, we have the vectors F1 equal to 8 minus 3, and F2 equal to minus 5, 2. So I call that script F. And I want to show that for any vector V equal AB in R2, I can write V as some linear combination of F1 and F2. So that means I want to solve the equation. See, what is xF1 plus yF2? That's Fx times 8 minus 3 plus y times minus 5, 2. So if I put that together, that's 8x minus 5y minus 3x plus 2y. And I want that to equal AB. So I have to try to solve the equations 8x minus 5y equals A, and minus 3x plus 2y equals B. So given any vector AB, I want to find x and y that satisfy this vector equation. So for example, so I just need to solve 2 equations and 2 unknowns. So any way you want to do it is fine. If I multiply the first equation by 2, and if I multiply the second equation by 5, and I add, I get x equals 2a plus 5b. And if I were to multiply the first equation by 3, and if I were to multiply the second equation by 8, and I add, I get y equals 3a plus 8b. So that says that any vector AB can be written as a linear combination 2a plus 5b times the vector F1 plus 3a plus 8b times the vector F2. And this representation is unique because I found if I want to write AB as a linear combination of these 2 vectors, these are the only possible coefficients. So it follows that the set F of the vectors F1, F2 generates R2. Every vector in R2 is a linear combination of them. And if I want to write AB, if I want to write 0, 0 as a linear combination, if A and B are 0, the only way to do this is 0 times F1 plus 0 times F2. So the set F1 and F2 is also linearly independent. And that means it's a basis. A basis for a vector space is a linearly independent set of vectors that generates the vector space. So that's the solution to part A. Now, for part B, I want to find the change of basis matrix. So I want to find a matrix P. So if I take a vector V, the coordinate vector with respect to F, and I multiply it by the matrix B, I get the coordinate vector for V with respect to E. So let's see, and how do I do that? Well, I mean, the vector, so remember the standard basis E is just the basis E1 equals 1, 0, and E2 equals 0, 1. So the vector F1, which is 8 minus 3, This is 8 times 1, 0 plus minus 3 times 0, 1. This is 8e1 minus 3e2. And f2, which is minus 5, 2, is minus 5e1 plus 2e2. So if I were to take a vector v, which was, say, x f1 plus y f2, and I want to write it as a linear combination of e1 and e2, this is x, and this is what f1 is, 8e1 minus 3e2, and y times f2 is minus 5e1 plus 7e2. So this is 8x e1 minus 5y e1 plus something times e2 minus 3x e2 plus 7y e2. Or if you like, 8x minus 5y minus 3x plus 7y, which is exactly what you would get if you took the matrix 8 minus 3 minus 5, 7, and multiplied it by the vector xy. So if I call this matrix P, this says that if I take P, and what is xy? Xy, if V is this linear combination of F1 and F2, what that means is that the coordinate vector for V with respect to the basis F is xy. So if I take the matrix P times the coordinate vector for V with respect to F, I get this vector, which is the coordinate vector for V with respect to E. If I multiply P times xy, I get this, and this is exactly, if I write the coordinates for V with respect to E, that's what that is. So that's what it means to say that P is a change of basis matrix. You take P times the coordinate vector with respect to the basis F. This gives you the coordinates of that same vector with respect to the basis E. So for example, P times the coordinate vector for E1 with respect to F, coordinate vector for E1 with respect to F is what? Oh, so I need to calculate that. So suppose I want to write E1 as some linear combination of F1 and F2. Well, I know how to do that. I worked that out right over here. So E1 is 1, 0. So 1, 0 is A is 1 and B is 0. This is 2F1 and B is 0 plus 3F2. And 0, 1, which is the vector E2, when A is 0 and B is 1, I get, so let's call these Q12F1 plus Q22F2. What are these numbers? When A is 0 and B is 1, this is 5F1 plus 8F2. So my change of basis vector matrix Q is going to be 2, 3, 5, 8. This is the first column. This gives the second column. So let's just do a calculation. What is P times Q? This is the matrix P, this is Q. So this is 8 minus 5 minus 3, 7 times 2, 5, 3, 8. If I multiply, I get 16 minus 15, 40 minus 40, minus 6 plus 6, minus 15 plus 8, I get the identity matrix. And you can check if I multiply in the opposite order, Q times P, I'll also get the identity matrix. So Q is the inverse of P. When you multiply PQ or QP, in both cases, you get the identity. So linear algebra. Page 262, number 1. So this is a very simple linear transformation. You take a vector and you just rotate it around the origin by an angle of theta radians. So you start with V, and then this rotation by angle theta gives you another vector. And the matrix for this rotation is cosine theta, sine theta, minus sine theta, cosine theta, for any angle theta. So if theta is pi over 6, rotation by pi over 6 has the matrix cosine pi over 6, sine of pi over 6, minus the sine of pi over 6, cosine of pi over 6. And you're expected certainly to know the sine and cosine of these basic angles. So the cosine of pi over 6 is √3 over 2, and the sine is 1/2. So this is the matrix for a rotation by pi over 6. If you're going to rotate by pi over 2, it's cosine of pi over 2, sine of pi over 2, minus the sine of pi over 2, cosine of pi over 2. And the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So you get this matrix. So this just means take a vector and rotate it by 90 degrees. And if this is xy, if you apply this matrix to xy, you get minus yx. So the vector xy, when you rotate by 90 degrees, is the vector minus yx. And if you rotate by pi radians, that just means that's pi. So you can imagine if this is xy, this is minus x minus y. And let's see what the matrix is. R pi is cosine pi, sine pi, minus sine pi, cosine pi. Cosine of pi is -1, sine of pi is 0. This is the matrix. And of course, if you multiply this matrix times xy, you get minus x minus y, just like the picture tells you. But this is the matrix for that linear transformation.
Okay, thank you so much, Dr.
Sure.
I get that.
We can use a unit circle for the angles, right? We don't have to know those values if we don't know them.
Well, You have to know them. I don't understand. I mean, what do you mean by using the unit circle? I mean,
Those are the values from the unit circle, right?
well, that's where the sine and cosine come from. They're defined in terms of the unit circle. But however you get them, so long as you know what is, you can calculate them, that's fine.
Okay.
I mean, you use these all the time in calculus.
Professor, you still having one more time?
7 o'clock tonight.
But no now, right?
Why?
I said you're still having a little more time now.
I'm sorry, I didn't understand what you said.
Like if you could solve any another problem now.
Of course. Happy
Okay,
to solve a problem if you have one.
I will explain. You know, before you start.
So linear algebra page 279, number 1. So I have this matrix, I'll call it A, which is 1 minus 1, 2, 4. And I want to find the eigenvalue. So I want to find the vector, I want to find the values of lambda such that for some vector xy, when I apply the matrix to xy, I get lambda times xy. So this is the same as saying, when I multiply this, I get x minus y, 2x plus 4y equals lambda x and lambda y. So this corresponds to solving the equations x minus y equals lambda x and 2x plus 4y equals lambda y. And if I just collect the x's and the y's, if I bring everything from the left to the right, I get lambda minus 1x plus y equals 0 and minus 2x plus lambda minus 4y equals 0. So I want to know for what lambda can I find a non-zero solution to this equation. So let's see, if I try and solve for x and y, let's say I multiply the first equation by lambda minus 4. And I leave the second, this is times x. And here I have minus 2x plus lambda minus 4y equals 0. And if I subtract the second equation from the first equation, these cancel, and I get lambda minus 4 times lambda minus 1 plus 2 x equals 0, or this is the same as lambda squared minus 5 lambda plus 6 times x equals 0. And if I want a solution with x different from 0, lambda squared minus 5 lambda plus 6, which factors, that's lambda minus 2, lambda minus 3, equals 0, means lambda equals 2 or lambda equals 3. So these are the only possible 2 eigenvalues. So let me look for eigenvectors. Suppose I take lambda equal 2. Then if lambda is equal to 2, this first equation says x plus y equals 0. And the second equation says minus 2x minus 2y equals 0, which is the same as x plus y equals 0. So if lambda is equal to 2, y has to equal minus x. So we get a vector v, which is x minus x, or x times 1 minus 1. So an eigenvector for lambda equal 2 is any scalar multiple of 1 minus 1. And let's just check. If I take the matrix A times 1 minus 1, that's 1 minus 1, 2, 4 times 1 minus 1. When I multiply, I get 1 plus 1 is 2. 2 minus 4 is minus 2. This is 2 times 1 minus 1. So the matrix times the vector is 2 times the vector. So this really is an eigenvector with eigenvalue lambda equal 2. Right? Is that okay so far?
Yes, it is, because that's the part important, that we can get that vector over there when we
All right, and now
factorize at the end.
let me find the eigenvector for lambda equal 3. For lambda equal 3, this equation is 2x plus y equals 0. And this equation is minus 2x minus y equals 0. So they're the same equation. It says y is minus 2x. So my vector xy is x minus 2x, or x times the vector 1 minus 2. So it should be that an eigenvector is 1 minus 2. And let me check. If I take A times the vector 1 minus 2, my matrix is 1 minus 1, 2, 4 times 1 minus 2. This is 1 plus 2 is 3. 2 minus 8 is minus 6, which is exactly 3 times the vector 1 minus 2. So I started with the vector 1 minus 2. I take the matrix A times that vector, and I get 3 times 1 minus 2. So 1 minus 2 really is an eigenvector with eigenvalue 3. So worked out okay.